Let's discuss what we have learned so far. So we have learned what is a fixed point, and we have defined, means we have learned and theorem how could we define a fixed point, how could we characterize the fixed point by its stability, whether it is attracting kind of fixed point or it is repelling kind of fixed point. Then thereafter, we have seen a mathematical jargon which is bifurcation. So, what is bifurcation? We have seen that. So, we have seen that bifurcation is a mathematical fancy word, but actually it does mean if I change something in, if I have something in my hand, means if I am dealing with some system, and if I change something very important to the system state will change completely. So as I one example could be the density of the oxygen in the available oxygen density in the earth could determine the body size of the animals who lived on the earth. We know that in earth in the very long ago the dinosaur was alive in the earth. So and there is a hypothesis that there is a lot of oxygen there. And Subhusaji, you could know better it, because I don't know about much of it about the hypothesis, but I have seen somewhere that there is a hypothesis that density of the oxygen could determine the size of the body of the animal who lived in the earth. So this is a kind of bifurcation from the large humongous body size to this tiny body size animal. So this is kind of the oxygen density kind of a parameter here, and if I change the parameter, then the system state will be changed from one state to another state. Another example could be the extinction of a population. So depending upon the growth rate of a per capita growth rate of the population, we could determine the system fate, and we know from our transcritical bifurcation. From that example, we know when r less than 1, the population will go toward extinction. So this means if per capita growth rate is less than 1, the population will go to extinction, and when the r become greater than 1, population will not go to extinction, it will go to a stable state. And the bifurcation point is r equal to 1. When r equal to 1, the system fate change from extinction to a means here this is a very tragic fate, from a very tragic fate to very comfortable fate. So that is that. So bifurcation means that now we have seen the transcritical bifurcation and saddle node bifurcation. And transcritical bifurcation, we have seen that only one fixed point appear from nowhere, and in the saddle node bifurcation we have seen that out of the blue simultaneously two fixed point occur. One is stable, one is unstable. Now today we are going to discuss the period doubling bifurcation. Period doubling bifurcation. So to begin the period doubling bifurcation, let us begin with this example where we model the population growth model by logistic equation. So xt plus 1 is r xt 1 minus xt. Here xt is the density of a population in certain region, and r is the growth rate. If you recall correctly, r is 1 plus mu, and mu is exactly per capita growth rate. This is per capita growth rate. Now, so far what we have learned, so we have learned that these when r less than 1, the only possible state is x star equal to 0. And when r greater than 1, we have learned it there is another fixed point. That fixed point is, if let's calculate that fixed point, so x star will be r x star 1 minus x star. So one fixed point x star is 0, another fixed point will be 1 is r 1 minus x star. That will be 1 minus x star 1 by r. So x star will be r minus 1 by r. So 1 is r minus 1 by r. So when r greater than 1, these become stable. From our intuition, we can say that this is right, because if I increase the r, if I increase the when the r will become greater than 1, when this mu become non-zero, means a positive number, that means if the system has any per capita growth rate, the population will not go toward the extinction. They will eventually avert the extinction or prevent the extinction of the population and go towards a population state where there are some number of individuals there. Now what our intuition says, if we increase, suppose the resource, and how the per capita growth rate increases, as we have assumed when we are dealing with this equation, when we are modeling this equation, we know if we increase the amount of resource, the growth rate, per capita growth rate of the population will also increase. Now if the per capita growth rate of the population increases, what our intuition says, if I increase the per capita growth rate, the population density should be going higher, because if I increase the per capita growth rate, what else could happen? More number of individuals are producing in the system. So what will be then the case, that the number of individual of the population should be going higher. That means x star should go from going towards 1. This is our, since x star could the value of maximum x star is 1. So if I draw this curve, so this is like a thing, so this is 0, this is 1. So one could say the maximum, when I increase the value, the population should achieve its maximum here. This is the f, this is the x. But is it the case, when if I increase further, suppose if I increase r further, will this fixed point remain stable every time? Let's check it. And what do we know the stability means? To check the stability, we have to find out the first derivative of this function. And what is the first derivative? T dx of r x into 1 minus x. So if you do it, you will get r 1 minus 2x. Now let's check T dx f of x at x star equal to r minus 1 by r. So this will be r into 1 minus 2 into 1 minus r by r. This is r minus 2 plus r. So this is 3r minus 2. So we have to check, since r greater than 1, we know for r greater than 1, this fixed point becomes stable. Now let's check up to which value of r it remains stable. Let's check it. So up to which value of r it remains stable. So, and we know the stability means Tx f of x x star to r minus 1 by r should be less than 1. So that means 3r minus 2 should less than 1. I think I did some mistake here. Should come up r equal to 3. Let's check it here. This is 1 minus okay. Oh, again I did mistake here. So this point is r minus 1 minus r. Here I put it wrong. This is r minus 1. If it is r minus 1, this will be 2r minus 2. This is r minus 2r plus 2r plus 2. So this will be 2 minus r, and this is right. So this is right. So then this should be less than 1. That means 2 minus r should be less than 1. 2 minus r should be less than 1. So this is the one thing, but that means this is only true. So we know that the modulus of this thing should be less than 1. So that means modulus of 2 less than 1. Now if it is greater than 1, if I know if, so let's check if, okay, let's check if r less than 2 greater than 1, in this range these become positive. So this is 2 minus r, so that means 2 minus r should less than 1. Then you will get this is r should greater than 1. So Bosachi, is it clear? Means if you don't get anything, just stop me there. Oh, okay. So then it is it is quite all right that if r greater than 1, then it will be always less than 1, and it is obvious if r remain between 1 to 2, 2 minus r should be less than 1. That is quite all right. Now if another case is if r greater than 2. If r greater than 2, what happens? If r greater than 2, then 2 minus r is less than 1. So the modulus means the magnitude, we have to take the magnitude. So that means magnitude will be r minus 2. So r minus 2 should be less than 1. Since if you this is 2 minus r become negative here, let me write it here. 2 minus r is negative for this case, and if it is negative, suppose negative 5, so we can't take negative 5 because negative 5 is already less than 1. We have to take the magnitude of the 5, so it is 5. So if you get minus 5, that means the system is unstable, so we have to take only the number 5. So here, since 2 minus r is negative, that means r minus 2 will be positive. So we are taking the r minus 2, and r minus 2 should be less than 1. Then the fixed point will become stable, and it implies that r should be less than 3. Then it is fixed. Then the fixed point is stable. So that means if r remains between 1 and 3, the fixed point x star equal to r minus 1 by r is stable. Otherwise it's become it's means, suppose this is drawing. So if this is r minus 1 by r, and if you will see when the r is remain between 1 less than n, then this fixed point is like that, this it will attract all the initial condition which is nearby, and if it does not remain in between, suppose r become greater than that, then it will become repulsive fixed point, so it will repulse all the fixed point. Now as our intuition says that if I increase r further, that means if I increase the growth rate, if I increase the r further, if r increases, the x star should increase. That is not quite right, so our intuition is failed here. So that's where come this beautiful mathematical thing, that from the nonlinear stability we will get and bifurcation, we will see that some other things will come here. Now could you guess what is the possible fate of the system if you see that two fixed point, that x equal to 0 and x equal to r minus 1 by r, they both become unstable. So Subhasji, could you guess what is the possible fate of the system now? Hmm. 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 Ha. Hmm. Exactly. Hmm. Right. Yeah, you are right. But here I am since here I want to say you that here these 2 points, you see the extinction point and the other point, both point will be unstable. Now as you are saying, it is right that the growth rate, if you see here, the growth rate will be at maximum when the population density is half, means half of the carrying capacity. If you say in the direction half of the carrying capacity, then you will see the population become the maximum achievable state, maximum growth rate or maximum population. Now the thing is, I want to know here that the system's extinction state and the remaining state, all these both of these two states become unstable. Now it is not it is not quite intuitive that now the system will show the periodic behavior, and which is not quite intuitive from our intuition. So that's where the mathematical theory comes. That's why the mathematics is so important for the to study the nonlinear dynamics. So how we will see that the periodic orbit has occurred. So what do we know about periodic orbit? We know one thing, that if let's check the period 2 orbit, so 2 periodic orbit. So we know that 2 periodic orbit means, so a point for the 2 periodic orbit means a fixed point of this will be a 2 periodic point. So if any x star satisfied this, means if I apply 2 times my map iteratively and the systems get back its initial state, then we call this x point x is the 2 periodic point. Now let's check it. To do it, I will use computer. So let me use 0. Okay, let me twin it by, wait for a moment. So let me first show you what will happen at r equal to 1.0. Means when r equal to 1, let's check it. We know that at r equal to 1, let's first from what we know, let's write it. What we know from, we know that at r equal to 1 there is a bifurcation, which is transcritical bifurcation, and if I increase r from 1, for r less than 1 only extinction was the possible fate of the system, and if r become r greater than 1, only the means extinction will become unstable. Now at what happens at r equal to 1, let's check it. At r equal to 1, you will see the system will go toward the fixed point x equal to 0. So because you see here, as we know, this is the identical line and this is our map fx. So this is our map f square x. Sorry, it is written wrong, but okay. This is at the y-axis it is f square x, and you see that only one fixed point is possible for f square x. How we know that? Where this identical line and this blue line, this means f square x, where they cut cross-sect, where they cut each other, that is called the fixed point. Now let's increase the r. So from 1 to 2, and we know that at r equal to 2 only one fixed point is possible, and you can calculate it. If I put here, let's put it here, r equal to 2, there are two fixed point possible. One is obviously x star is 0, another is x star is this 2 minus 1 by r minus 1 by r, means 2. So this will be half. And you don't confuse that why I am using this fixed point, and this fixed point is corresponding to this period 1 point. So this fixed point is corresponding to, if I solve this equation and I get these two equations. Now if one can confuse about these things, so now we are talking about the solution of this equation, f of x equal to x, not fx equal to x. So why we are using these two as a solution of this equation also? This is very simple, because if it satisfied this equation, then we know f of x will be f of x, and we know f of x equal to x. So that means if any point satisfied this equation, it will also satisfy this equation. That's why we are saying that only two fixed points are there, and which are the fixed point of f of x, and no new fixed point appears. So let's go in this direction. If I increase, and we know that only two fixed points are there, so one is at 0 and another is half, and you see only at r equal to 2, we know that r equal to 2, x star equal to half is stable. That's why it's going there. Now let's check what happened at r equal to 3, and we have seen that at r equal to 3 the both fixed point will lose its stability. So let's check it, what will happen at r equal to 3. So you see that at r equal to 3, one interesting thing happens. You see, this is f square, this is not fx. Don't confuse that this is a previous graph. It is, if I iterate 2 times a single point, what will happen then? That is this curve. So this is showing one thing, that for mu equal to 3, or this is r equal to 3, sorry, this should be r equal to 3. You see, there are 2 hills and 1 valley appears. Now, and similarly, previous there was no valley, and another thing is that at this fixed point, this is a fixed point, since identical line cut at this point, but you notice one thing, that this identical line become tangent at this point, and we know the tangent means differentiation, and we know that at this point the differentiation, first derivative of the curve with respect to x become 1. That means there is a bifurcation, and this bifurcation is called the periodic bifurcation, because you see here, you see a single initial condition goes to a single point, right? That means it is a period 1 point. A single 1 point goes to a single point, it will remain stay there forever. Now let's see what happens if I increase mu further. So you see, mu further means suppose 3.5, let's 3.5. Now you see one interesting thing. Okay, now you see one interesting thing. Now you will see the fixed point, what happens. So what happens, so we'll see here, but let's see here that now you see the point will not stay in a single point, it is oscillating between 2 points. So that is called the bifurcation. So from period 1 the system will become periodic, and it become period 2, period 2, because it's actually oscillating between these 2 points. So this is called the period doubling bifurcation. From one single point to it's become the fate of the system become 2 points, and the system will oscillating between 2 points. Now this is called the period doubling bifurcation. Okay, and you see there are new 2 fixed point appear. One is the previous fixed point of f of x. This also the fixed point of f of x. Now 2 fixed point appear because of this valley got deeper, and this the height of the hill become increased so much. That's why increase that's cut this point and this point. So let me explain it further. So what happens here? So you see, so this valley increased and increased the height, and the deep will, so previously it was like this, so it is not quite right. So you got, so suppose like this. Now what happens, if I decrease it, decrease the valley means the deep the valley, and if I increase the height of the hill, you will see another 2 fixed point will appear. One is here, another is here, and it was there from the previous, this is the fixed point of f of x equal to x, and if it is 0, then it is also the f of x equal to f of x. Now another fixed point comes, which is the fixed point, which is the only unique solution of this equation, and this if I go back to my code, you will see the system is oscillating between these 2 points. So oscillating between, so you will not seeing these 2 points, but it is actually oscillating between these 2 points. So there will be 2 points. So these 2 points are the fixed point. Now you will not see that, because this is the f square x fixed point. So you will see that they are oscillating between these 2 fixed points. They actually will go, this point will go here and this point will go eventually. So that's it. Now let's check this is Sobusachi, is it clear that the how the period 1 means period doubling happens. Okay. Okay. So, and it is one thing is there, that is that our intuition is not quite, means we cannot achieve the oscillation by our intuition. Intuition tells us either it will go to extinction or it will go toward the stable fixed point. But you see that where because our intuition always works as a linear way, so that's why the nonlinear system is so interesting, and we have to know this bifurcation or this kind of thing to know what is the fate of the system, to explain what is happening in the system. So this is thing. Now let's one thing let me draw, that is called the actually called the bifurcation diagram. You will see in the many textbook this is bifurcation diagram. So in bifurcation diagram what we will do, so in y axis we are all the fixed points, and in the x axis we are draw the parameter. So you see if it is 1 and it is 3, see here up to 1 there is only one fixed point, which is x star equal to 0, and then from r equal to 1 there will be another fixed point. This is like this will be like this is this fixed point is this fixed point is x star is r minus 1 by r. Now you see this is r equal to 3 and it continues to exist, but from r equal to 3 stability becomes unstable. Now what is happening here, you will see this is remaining there, but from r equal to 3 there are another two fixed point appears, which is like this and like this, and this also stay there, but it become the fixed point is there but it become unstable. The fixed point is there and become unstable, so this is the bifurcation diagram. So let me first algebraically show you that the existence of this period doubling fixed point means, let first there exists, let me mathematically prove that. So we know that f of x, we have to solve this equation. Now this means we know that f of x means mu. We are using r f of x 1 minus f of x will be x. If I put here the value of that r x into 1 minus x 1 minus r x into 1 minus x into x, this is r square into x into 1 minus x minus r cube x square to 1 minus x square into x. Now know that the two solution of this equation we know as since we know from this here there are already we know the two solution, one is x star is 0, another is r minus 1 by r. So the two solution is x star equal to 0 and x star equal to r minus 1 by r. So that means from here we'll get things, if I divide by x star, so we'll get here r square 1 minus x minus r cube x 1 minus x square equal to 1. So this is r square minus r square x minus r cube x 1 minus 2x plus x square minus 1 is 0. So this is, let me write it, r square minus r square x minus r cube x plus 2r cube x square minus r cube x cube minus 1 is 0. So this is r cube x cube x cube, then is plus 2r cube x square, then this r into r square, so r plus 1 into x, if I count this 2, so if I take this one, I take this one, I take these two, I have to take this one, so plus r square minus 1 equal to 0. Now we know that since this is a solution, so that means x star minus r minus 1 should equal to 0. Now how you will get this x star minus r equal to 0? So we know that if it comes like this, x star minus r into some other series is 0. If it comes, if it would come, suppose if it would come, so it is our hypothesis that if it would come like this, then we can say that then x star minus r minus 1 could be 0. So this could be a possible solution. Is this line is clear? Suppose then we can go further. Okay, so if it is clear, now you see that if I take 1 x star here, means 1 x here, so not write it x star. So if I take 1 x here, so if I x from here, so from x cube it will become x square. So this qx series should become, the maximum power should be x square. So let's suppose that qx is ax square plus bx plus c. Now let's solve this equation. So this is our hypothesis. So let's check. So x minus r minus 1 by r into ax square plus bx plus c equal to 0. So this, if I simplify it, ax cube plus bx square minus c r minus 1 by r minus a r minus 1 by r x square minus b r minus 1 by r x minus c into r minus 1 by r equal to 0. So this is ax cube plus b minus a r minus 1 by r x square and where is the x? This will be somewhere, should be plus cx. So plus c minus b r minus 1 by r into x. This is, I have counted it twice. Right, x is ax cube, bx square, cx. This is minus ar minus 1 x square. This is minus bx. This is minus c r minus 1 by r equal to 0. Now you see, if it would my equation, so this and this should be similar, this and this should be same. So if, let me write it, let me draw a box around here in the blue color. So if my hypothesis is this, then this equation and this equation should be same, and if this equation and this equation has to be same, then my coefficient of x cube should be x cube, every x cube, x square, x and x to the power 0 should be same. That means a should be equal to minus r cube. And you see why, means you first of all the motivation will not be clear why I am doing this thing. So the simple thing is, I want to check whether or not there are any fixed point other than these two. So I am using these two fixed point. First of all, when I divided the x star, so I am using this fixed point, and now I am using this fixed point to check whether or not there exists any other fixed point. So if there is any other fixed point, we will, from where we will get that fixed point. So by solving, one fixed point could be this, and another two fixed point will be the solution of this equation. So that's why I am after solving this equation. That is our motivation. So let's now b equal to, how will we calculate? So b should be b minus a, I know. So if I put a, r cube into r minus 1 by r, it should be here 2r cube. So this will be b, this is r square, so minus r cube, okay, minus r cube plus r square equal to 2r cube. So let me check whether I am not correct or wrong. So this is 2r cube. Okay, this is minus r cube, so this will be plus. That's why I am checking. This will be plus, so there is minus. So this is like p will be r cube plus r square. So if I take r square common, r plus 1, b will be that. And now let's check the what is the value of c. C minus c r minus r, if I equal to x0 should equal to this r square minus 1, r square minus 1. So this will be c will be r into r square minus 1 by r minus 1. Also this is simply r into r plus 1, because r square minus 1 could be thought as r plus 1, r minus 1. So now you see we can write another equation which is qx. So if it was our hypothesis, now we get the form of qx. So if we could write, then that means we could write this equation in this form. And what will be then qx? The qx will be a x square, r cube x square, b means r square into r plus 1, bx plus c. You see here is a minus is there, r into r plus 1. So that's all. So if I know the form of qx, now you see that means we can write our hypothesis quite right. We could write this equation in this form. So one from here we can write that one fixed point is this, and other fixed point will be by solving this equation, solving qx. So if solving qx means this is 0. Now let's solve this equation. If you solve it, r cube x square plus r square r plus 1 x minus r into r plus 1 equal to 0. So this will be plus, this is minus, this is minus, this is plus. So here not x cube, this is x square. So here we know a formula which is called Sidor-Acharya formula, x equal to plus r square by r plus 1 minus b plus minus root over of b square r to the power 4 r plus 1 its square, b square minus 4 ac 4 r to the power 4, this is c, this is a, r plus 1 y 2 r cube. So this will become r plus 1 by 2r plus minus, Here from r square I also take r square common, 1 by 2r root over of r plus 1 minus 4 of plus 1 plus minus 1 by 2r root over, we take this is r plus 1 common, r plus 1 minus r minus 3. You see, now you get two fixed point. One fixed point is r plus 1 by 2r plus 1 by 2r root over r plus 1 r minus 3. That is one fixed point, and another fixed point is by taking this negative sign into account. Now this is the two fixed point. Now you see when this fixed point will come. There comes one interesting thing, that when r greater than, we know that r greater than 0. If r greater than 0, then means r plus 1 greater than 0. Now you see, that means to appear this fixed point, we know that if root over of minus thing is imaginary, this is imaginary, that means if something like this appear, that we will say that in reality that number is not exist. So that means if under the root that should not be become negative, that means r plus 1 into r minus 3 should not be become negative, it should become positive. And since this is a positive number, and we know from positive into positive become a positive number, so that means this should also become positive, r minus 3 should also become positive. And if r minus 3 become positive, from here you will get that r should be greater than 3. That will say that if r become greater than 3, then only these two fixed point will appear. And we have seen from our computer application that it is quite true that for r greater than 3, the another two fixed point appears. And other times only two fixed point was there, one is x equal to 0 and then other is r minus 1 by r. That is it. Now is it clear, Subhutaji? Means I know it is quite mathematical things, means mathematical algebra. Okay, now we will see the stability, then I will end this class. Okay, now let's check what is the stability of these two fixed points. Now could we check the stability of this fixed point by differentiating fx? No, we could not, because this is not a fixed point of fx. You see, this is not a fixed point of fx, this is fixed point of some function gx, which is f of x. So we have to derivative this one, we have to take the first derivative of this function. And if I take the first derivative of this function, I have done it, and it will be like that: f prime of f of fx, f prime of f of fx and f prime of x. So if I put gx any point x equal to x0, so then if this is two periodic point, this will be f prime of x0 become x1 and f prime of x0 become x0. So if I apply f on any one of the fixed point, it will generate another fixed point, so that is x1. Suppose x1 is here r plus 1 2r plus this thing, and x0 is r plus 1 by 2r minus this thing. So if I apply f of x0, it will give me x1, and if I give f of x1, it will give x0. So that's all. Now that means we have to put the value here. So we know the f prime value, that is this is f1 minus 2x1 and another is 1 minus 2x0. R, so basically r square. So first of all let's check 1 minus 2 of x1. Suppose x1 is, let me write r plus 1 by 2r minus 1 by 2r root over of r plus 1 by r minus 3 3. This is another thing 1 minus r plus 1 2r plus this 2 has been cancelled plus r root over r plus 1 by r minus 3. Now you can see this can be thing as a and this a minus b and this is a plus b, so you can write it r square into b square 1 minus r plus 1 by 2r its square. I think this is not there because 2 is multiplied by that, so this is not there, this will be not there. Okay, plus minus these things square, so this is 1 by r square r plus 1 into r minus 3. Now r square, this is r minus r plus 1 by r square, this is 1 by r square to r minus 3. So this is cancelled, so this is 1 plus r plus 1, so I think this is a minus, minus r plus 1 minus r plus 1 into r minus 3. So this will be, if I simplify it, it will become r square minus 3r plus r minus 3. So this will be 1 minus r square minus 2r minus 3. Now if I take 4 minus r square minus 2 r square minus 2r plus 1 and minus 1, so minus 1 plus 5 minus this will become r minus 1 square. So this is it. So if you do a derivative, that means whether or not the 2-period orbit is stable or not. So to check that, we know that we have to take the derivative, so we have done that, and it is quite a tedious calculation, but it is the thing that we have to do for checking the stability of 2-periodic orbit, and we got this simple result. So that means this is the thing. Now let me what I am saying. So that means when it will be stable, when this derivative, suppose this is right at g prime x star, then if g prime of x star modulus of g prime x star it become less than 1, then we can say that 2-periodic orbit is stable. So when it will become stable, so let's check it. So that means root over 5 minus r minus 1 square is less than 1. So it could be two cases. One is that 5 minus r minus 1 square is less than 1. Another case is r minus 1 square minus 5 is less than 1. Two cases could be possible. So here, from here we'll get, so okay, minus 5 r minus 1 square 1 minus 5, so this is r minus 1 square should be less than minus plus 4. So here its sign will be changed. Okay, let me do it in this way, it will be clearer for understanding. Minus 1 less than minus 4. So you see both numbers are minus, so you know that minus 2 is greater than minus 4, but if you want to take the only the value, not the sign, so but you see that 2 is not greater than 4, 2 is less than 4, so that means this sign should be changed. It will become r minus 1 square should greater than 2. So greater than 4, so this means r minus 1 should greater than 2, so that means r greater than 3. So it is that the thing that is appearing. So if r become greater than 3, then the 2 periodic orbit becomes stable, and what we have seen numerically means by computer programming. Now let's here this case, this will be r minus 1 square less than 6, 5 plus 1 6, and this is r minus 1 square, means r minus 1 should be less than root 6, so this is r should less than 1 plus root 6. So it give another range. So just like the previous range, it also gives another range r. So for only this range, the 2 periodic orbit remains stable, and if the r going outside this range, the 2 periodic orbit will not remain stable. So if I go back to our previous bifurcation diagram, suppose here somewhere this is 1 plus root 6, so after this point, this periodic 2 point will not remain stable, this will become unstable. This is previously become unstable. Now you see here also, you see all the fixed point become stable. X equal to 0 unstable, x star equal to r minus 1 by r unstable, and period 2 point also become unstable. Now from the symmetry we know that, so that will come later, that what happens after this point. You will see from the symmetry that if I as it is happening here, so from this fixed point become another period 2, this after when this become unstable, period 2 orbit appears. So here also when it become unstable, you will see here another 2 period stable 2 period will appear, here another 2 period stable appear, and it will go somewhere and become unstable. This is called the period doubling cascade. So every time you will see that this period doubling happens. But let's not confuse about it. Let's focus what is here. So first of all, we have checked that one bifurcation happens when for 0 to less than 1, x star is only extinction is possible. Second, we see that 1 less than 3, there is x star is r minus 1 by r stable. And third, we have seen now for 3 greater than r less than equal to 1 plus root 6, only x star is period 2 point, so x0 and x1. So this is called the period doubling bifurcation, and you will see as I am hinting toward that. So you will see that these kinds of period doubling happen again and again, and from here if you see from 1 period it become 2 period, and from 2 period it will become 4 to 8, 8 to 64, and 64 become unstable, and so forth and it will be going on continuously, but it will not go infinitely. You will see at r equal to 4, all the periodic point will become unstable, and you will see the chaos will appear. So since the all periodic point will become unstable, and there will be no stable fixed point at all in the system, this trajectory will become chaotic, and it will roaming around in the phase space here and there. So that's it. Is it clear, Sobusaj? I know from here the class will be going to little bit mathematical, but if I can give example anywhere, I will give, but somewhere I need the help of mathematics to see the underlying things that will be not intuitive from our common sense. Okay, so then let's end the class here. We'll meet Monday. Okay. Okay, thank you.